In this video, we'll look at some results for shock angles that form in a hypersonic flow. The small Drummond reflected shock tunnel, located in the Centre for Hypersonics at the University of Queensland, was used for the experiments, from which I'll present some results here. The Drummond tunnel is the tunnel that David Gilfind described earlier when he introduced the Schlieren technique for visualising shockwaves. The tunnel was set up to produce flows in the test section at Mach 6.8, so the flows are hypersonic. We inserted into the test section some two-dimensional wedges that caused the flow to deflect through different angles. Wedge angles of 10, 20, 30, 40 and 45 degrees were used. We then used Schlieren imaging to look at how the shock angles varied for a fixed flow Mach number, but differing flow deflection angles. In the notation we've been using, we have a fixed oncoming Mach number m1, and we vary theta, the flow deflection angle, to see how beta, the shock wave angle, will change. So here's the result for the 10-degree wedge. The flow is from left to right at an oncoming Mach number of 6.8. The 10-degree wedge is seen as the dark shadow at the bottom of the image. We can see the oblique shock wave being generated at the tip of the wedge and passing up to the right. The shock wave remains attached to the tip of the wedge. At this relatively high Mach number, the oblique shock wave is inclined at a relatively low angle to the wedge. Note that the shock wave is straight. The wedge angle has been increased to 20 degrees in this experiment. We see that there's a corresponding increase in the angle of the shock wave. Again, the shock wave is straight. If we superimpose onto this image the trace of the shock wave for the 10-degree wedge from the last image, we can clearly see the increase in the shock wave angle beta at which the shock forms for the higher wedge angle. Next is the 30-degree wedge. A shorter wedge is used when we come to 30 degrees so that we can keep the shock and the wedge within the region of flow in the tunnel that's uniform. The shock is inclined even further, as we'd now expect. The shock is still attached to the tip of the wedge. Despite a little bulge where the shock first forms, the shock is essentially straight again. And we can see how the angle is increasing by superimposing the shock angles for the 10 and 20 degree wedges. The wedge angle is increased to 40 degrees. The wedge is even shorter now. The oblique shock wave still starts off straight. There's a curve in the shock out here as indicated. This occurs because an expansion from the corner of the model is catching up with the shock wave. However, this is not significant for our discussion at present. We're only interested in what happens to the shock wave prior to this interaction with that expansion. Again, we can put in the progression of the shock wave angle beta for the different wedge angles. Finally, we have the 45-degree wedge, and now we see something very different. The shock is very curved and is actually just standing off from the tip of the wedge. This shock wave is a detached shock. Note how the shock wave is normal to the flow near where it detaches, and that the angle of the shock wave progressively reduces away from the wedge. So, experimentally, we've demonstrated that an oblique shock wave will eventually detach if we push the wedge angle up to a high value. For completeness, here is the progression of the shock angles we obtained for wedge angles from 10 degrees up to 40 degrees. From our analysis of oblique shock waves, you'll recall that we can plot beta, the shock wave angle, as a function of theta, the flow deflection angle, for any given Mach number. Here's the plot we had earlier. We have beta on the vertical scale and theta on the horizontal scale, and we're showing curves for different Mach numbers. In this case, Mach numbers of 2, 3, 5 and infinite. Let's add the curve for Mach 6.8 onto the plot. That's the Mach number in our experiments in the Drummond tunnel. So along this curve, we could look up what angle shock wave we'd expect for each of our wedge angles. So here is the point on the curve for the 10-degree wedge, for the 20-degree wedge, the 30-degree wedge, and the 40-degree wedge. For each of these, we can read off the theoretical shockwave angle. If we look at the maximum flow deflection angle, for which we'd expect to get an attached oblique shockwave, we see that for Mach 6.8, we would expect theta max to be just over 43 degrees. So we'd expect that our 40-degree wedge would produce an attached shockwave and that our 45-degree wedge would produce a detached shock. And that's what we see. We see the characteristic straight shockwave for the 40-degree wedge on the left and the detached and curved shock for the 45-degree wedge on the right.